Good afternoon, everyone. Today we're going to do Chapter 5. And in Chapter 5, the topic is probability. 5.1 is the introduction to probability. And then there's some probability rules we'll get into in the later sections of 5.2 and 5.3. But right now, we'll just start off with the introduction of probability. Idea of the likelihood that things happen. Let's just start out with just a basic example. I've got 3 red marbles and 7 blue marbles, and they're in a bag. And I just shake up the bag, right? And they get all random. And my question is, what's the probability that I select? I'm going to select one marble, a red marble, from the bag. And that's what we're going to answer. We're going to answer that question. What's the probability that I select a red marble from the bag? I'm going to select the one marble, pull it out. Well, what's the probability it's red? And so with probability, we always write these fractions. Everything's a fraction. What do you think goes in the denominator?
10.
Yes. The total number of events in this sample space. That's how they say it. Yeah, so there's 3 red marbles, there's 7 blue marbles, there's a total of 10 marbles, right? I'm going to put that in my denominator. You can just put 10, but you think there are 10 marbles possible. All right, 10 total marbles. And the way we say in statistics with probability here, the way we discuss this, we say, you know, the sample space. There are 10 elements in the sample space, and that's the number that goes in the denominator. What goes in the numerator?
3.
3. The number of red marbles possible out of the 10 marbles. So we get 3/10. And you could actually leave your probability solution as 3/10. But some of you like to write it as a decimal. 3/10 is
33%.
0.3.
3.
Now, if you write that in terms of percentage, is it 3% or 30%?
33.
That'd be 30%, right? So when 3 out of 10, 0.3 is also 30%. Well, all these are fine. But make sure for this, so when you take that 0.3, you can move the decimal place 2 places. Some of you just figure out, well, I'm going to take that 0.3, multiply 100, you do that too. Just be careful though. 0.03 is 3%, right? 0.3 is 30%. So hey, just real quick, that number, what percent is 0.5? 50%, very good. That would be 50%. Whereas 0.05 is only 5%. And my goodness, what would 0.005 be? Yeah, very good. Did you hear that? Outstanding. You said 0.5%. But you can leave your answer as 0.005. You can leave your answer as 0.5. It's just when you write your solution, you can actually write it as 3/10 or a reduced fraction. 7 out of 24. My odds of winning the lottery, 1 out of a million. Right? You can write it that way. But just be careful when you're writing in terms of percentage or just writing it as a decimal. One other thing, we're going to start seeing these types of numbers appear more often in this course. Is numbers like this. I'm just going to write 3.022. And so that can't be a probability. That can't be a probability. The highest probability possible is 100%. Right? Yeah, we know there's things in this world that can like increase over 100%. When we're talking probability, the highest possible is 100%. Well, what we were just talking about, wouldn't that be 300%? So yeah, that's not a probability, but you're going to see numbers like this occur more and more often, and they're going to emerge on your calculator. These are going to be your probabilities. So this right here, when you see this on your calculator, this is in scientific notation. All right, so I wish they highlighted this on a calculator, but it'll be sitting at the end of the calculator. So 3.022, maybe some more numbers, e negative 4. That means 3.022 times 10 raised to the negative 4. Which also means that when I've got a 3022, and that decimal point that was right here moved 4 places that way. So what I'm going to do is I'm just stick some zeros in front of here. Here. I'll stick too many, but the decimal place that was right here, it moved that way. How many places?
4.
So it starts having to go 1, 2, 3. Oh, there it is. Let me make a big dot. Take all these off. So really, that number right there is 0.0003. A very, very, very small chance, right? I mean, that's the odds I get in an accident today, right? On my ride home. It could happen, but you know, we're hoping it doesn't. Those are my chances. So it's just a very small probability. So would you look out for that? Now when you're looking at your calculator, look at the end. Look at the very end. Who's got the newer calculators? Some of those I like that they, the screen, it actually shrunk it a little bit. You can spot that a little bit easier. So just be looking out for that. You'll know, you say, man, you can't get 300%. So very good. I guess what's an easy way to do this? If you see negative 4, then how many zeros will be before that 3 after the decimal point? 3, right? So if that helps. So if you had this number, 6.22 e negative 5, well then I'll just put a decimal point. If you want to write this in decimal formation, that means there would be 4 zeros after that decimal point, and then that number 6. Does someone see that? 4 0, negative 5, 3 zeros, negative 4, if that helps. The key is, you know, they're very small numbers, aren't they? Just know that. They're very small probabilities. Some of you take chemistry. I think you've heard of 6.022 times 10 to the negative 23rd. That number is puny, right? Yeah. All right, so I'll erase this. All right, so I'm going to put on the board a probability model. Or excuse me, we're going to create a probability model from a frequency distribution. That's what we're going to do. So I'm going to pull a frequency distribution from section 5.1. This is on page 267. And I'm just going to create this probability model with you. But what I'm writing on the board right now is just a frequency distribution. This is actually problem number 38. All right. Number 38. They've got age 15 to 19-year-olds. All right. 20 to 24. 24 to 29. 30 to 34. 34 to 39. 40 to 44. 45. They went all the way up to 54 with this last one. Okay. Those are 8.
Professor, that should be 25 to 29.
Oh, thank you so much. Well, that's a 25 to 29. Thanks again, Art.
No problem.
So these are the ages. Over here, we have the number of multiple births. Cool. Oh, Brianna.
Wasn't it the same down there? It should be 35 to...
Ah, Brianna, thank you. I didn't do it anywhere else, did I? Let's see, 35 to 39. Thanks, Brianna. This is the number of multiple births. And by this term, multiple births, they're talking about those individuals who had at least 3 kids or more, triplets or more. So I'm not talking about twins. So if someone had twins, all right, now that could be multiple births, right? Multiple, two at once, but we're talking about triplets or more. All right, and here come the numbers. This is a frequency distribution. We've seen plenty of these, 100, 467, 1620, 2,262, 1,545, 328,105.
Is that per 100,000?
What was that?
Is that per 100,000?
500,000.
Number of model 3 or more bills. It don't tell you that.
No. Hey, this source, everyone, this was National Vital Statistics Report in August of 2010. So it is national, so they're talking about the United States. These are multiple births, United States, 3 or more babies at once. I'm curious, anybody in the class knows someone who's had triplets? Anybody? Isn't that interesting? Doesn't occur often, does it? Because we all have friends and know people who have had babies, of course, right? We know people, but no one in this class seems to know someone who had 3 babies or more at once. I know one person. I only know one person. I had triplets, actually. Hey, come on in there, son. So these are multiple births. What we're going to do is we're going to construct a probability model. All right. And we're going to construct a probability model. All right. The good news is you're going to know exactly what to do. You and I are going to put the probability model right next to this. And you already know how to do this. Because you did something like this on test 1. Do you remember relative frequency?
Mm-hmm.
I'll say it again. Remember relative frequency with the percentages? That's what we're going to do. It's going to be the same step-by-step procedure. Cool? So we're going to come up with these percentages. Just, okay, what's the likelihood, a random person who does have multiple births, in the future, you could say what's the chances that that person would have that. All right. So let's come up with these here. Hey, for our class presentation here, when we come up with these, at some point, the calculator is going to write these decimals out to many places, right?
Mm-hmm.
How about each one of these, we'll round to 2 decimal places. That's what we'll do. We'll round each one of these 2 decimal places, and then we'll just make sure everything adds up to 100% because we'll be rounding in there. So, what's step 1?
Add all of them.
All right, we got to add them up. We're going to sum all these here. I'm going to put that down. That's that summation symbol.
6427.
I hear 6427. And Holland verifies that. Thank you, both of you. Everyone, they're getting 6,427 for the sum. That's the sum of all these. Now, we just want to make sure we don't do this backwards, right? I'm going to type this on my calculator. Do I type 100? Then I hit the division sign?
Mm-hmm.
And then the 6427, or vice versa?
Yeah. Then
I'm going to type it like that, right? Oh, good. So that's how we're going to type it on our calculator. What comes up? Just give me like the first 3 numbers after the decimal place.
0.015.
0.015. What do you all think? If I'm going to estimate that round it to 2 decimal places. What do you want to do? Want to do 0.02? Will that work? Awesome. Hey, could I have rounded that down to 0.01? Yeah. Could you leave it 0.015? Absolutely. Absolutely you can. But I just thought for our class demonstration, we'll just do all these to 2 places. Now, some of you might write that as 2%, right?
Mm-hmm.
Some of you may prefer to write it that way. I'll write all these in decimal form. All right. So when 2%, ages 15 to 19 had multiple births. All right. How about this one?
0.072.
I'll make that 0.07. What's this one?
0.25.
Ooh, I got another one that's in the middle. See the 5, everyone? So I'll just go to 0.03. Again, though, 2.5%. I could round that to 2 or 3%. I'm going to round up to 3%. And now, each time I do this, we're taking that number, dividing that number. That number, divide that number. All right, what's the next one?
Shouldn't that be like 30%? No,
Yeah,
3%.
it's 0.25.
Oh, thank you. This was 0.25.
Yeah.
You all know the best. So I'm going to make that a 0.2. What was after the 5? 252. So I'll write that as 0.25. What do you get for the next one?
0.35, 352.
All right. Next one.
0.24.
0.05. What was after the 05?
1.
And lastly, another 0.02. Now, if I add all these up, and they add up to more than 100%, I think I'll go back in and either this one or, what does this one do? 0.01 what?
0.0163.
You know, maybe this one I'll tweak down to 1% if it doesn't add up to 100%. All right, that's 7, that's 9, plus 25, 34, 69, 89, 93, 98, 100. I think we got 100%, right?
Yeah.
These sum up to 1.0. All right, we're good. I'm gonna put my smiley face. We're good to go. And there's my presentation. I'm gonna put that in my presentation. Just to give rough estimates of what each of these percentages are. 2% of the multiples were ages 15 and 19. This is interesting. So on women, 40 to 44, 5%. That's pretty high for women. 40. What do you think's going on there? Anybody know? I know there's nurses in this room.
In vitro.
Yeah, there you go. Exactly. Very good. Very good. So these are multiples. This is called the probability model. So we're saying, yeah, roughly 35% of those multiple births, ages 30 to 34. Cool. Hey, we're now going to get into the probability rules. And in 5.2, they start talking about the addition rule. All right. Well, before I write the addition rule down, we're going to start with an example. Can I raise? Yeah?
So, Professor, you're not doing the law of large number, like where it converges to half and all this?
No, but we'll discuss it.
Okay.
We'll definitely discuss that. That's going to come up in our discussion, so very good. And when Art just mentioned the law of large numbers, which is an interesting law, what page did they present that on?
First page, let me see, 255.
So on page 255, and when they do have something called the law of large numbers, I'd like to read this to you. But this will come up through our class today, next class, through our discussions. And they say, as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So you're like, what does all that mean? And when roughly about, I'm a lefty, but I think about like 13%, about 13% of the population's lefty, right? But if you just got like a small sample, you might have like a bunch of lefties in that little small sample. Okay, so I'm talking about like 25 people. You go, hey, how many people's a lefty? You might get more than that, what, 12%? But if you looked at like 500 people all at once, random people, and you try to figure out what, all right, and you ask a whole group of people, hey, I have an announcement. Who in here is left-handed? And those people raise their hand, they count them up. With 500 people, that percentage would be very close to what that, actual proportion is, which is roughly about 12%. Cool? Hey, I'm just curious right now, because I'm a lefty. So I'm going to include myself in this bunch. Who's a lefty? All right, we're going to count them up. Me, 1, 2, 3, 4. Yeah, lefties rule. All right, we got 4. Now I'm going to count up how many we got here. I'll be real quick. Myself, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right. What's that on the calculator?
1/7.
What's 1/7? I'll squiggle it. Let's just see. About 13% or so is lefty.
About 14.28.
Ah, it was a little higher, huh? I was like, whoa, that's kind of high. A little bit higher. It was a little bit good. It was very close, right? But you watch, you do that with like 500 people, be more to that 13%. And that's what we're talking about, the law of large numbers. Right? Funny things can happen in small sample sizes. But when you're talking about what? Large groups, right? That's what happens. So we'll even talk about anybody in here plays lotteries. You know, maybe I just take one shot at winning the lottery. Oh, maybe I get lucky and I win. But what if I'm, you know, one of these play it every day types? Well, then everyone, the odds of me winning, you know, the amount of times I will win will be right along with what the probability of winning is. That's what we're talking about with law of large numbers. Okay. So we're going to talk about the addition rule for probability. So to do this, just to understand the basic rule, it always helps with cards. So I'm going to put on the board these cards, at least write them some stuff about it, because I'm going to have someone in this room who's not a card player. You might be like, I've never played cards in my life. But just with these cards, we can get a better understanding of the probability rules. All right, so there's a total of 52 cards in the deck. There are 4 suits. So let me just write cards over here. There's 4 suits. What are the suits?
Clubs.
Hearts,
Oh.
diamonds, and spades.
Outstanding. Clubs, spades, diamonds, and hearts. All right, so those are the 4 suits. If you've never played cards before, when there's 4 suits, you got hearts, diamonds, spades, and clubs. And there's a total of 52 cards. So 52 divided 4 means there's how many clubs?
13.
All right, so there's 13 clubs. There's 13 spades in the deck. There's 13 diamonds. There's 13 hearts. The lowest number is 2. So you got like a 2 of clubs, and a 3, then a 4, then a 5, 6, 7, 8, 9, then a 10 of clubs. And then you have a jack. So a jack has a face on it. There's an actual face on it. Then there's a queen. The queen has a face on the card. There's a king. The king has a face on the card. And then the last one is a
Ace.
ace. So I'll just put A for ace. And each one of these suits have these. So there's a 2 of diamonds. There's a 4 of diamonds. There's a 5 of hearts. There's a 6 of hearts, right? And there's a total of 52 cards in the deck. So I just wanted to show that to you. If you wanted to see them, you're like, can I see your cards? You know, I've never seen these, but there's an image in the book. You know, because I sometimes get people like, I never played cards. On page 260 is dice. On page 260 you'll see some dice, but you'll find the cards shown on page, let me flip a few more. I just saw the dice. Where are cards? Page 271. So I just want to point that out. You just want to see an image of all those cards laid out. Page 271. So these are the cards. I do want to point out which ones had faces on it. The jack, the queen, and the king are face cards. So if there's 3 of these, 3 of these, 3 of these, and 3 of these, do you agree there's 12 face cards in the deck? So I'm just going to point that out. That one, because the textbook might mention face card. I didn't want you to be at home doing a homework problem going, what the heck's a face card, right? So you got face cards. These are all the cards in the deck. Total of 52. One other thing, the colors. Half the deck is red cards, half the deck is black cards. So the hearts and the diamonds are red. So all these are red. The diamonds and the hearts are the red cards, the clubs and the spades are the black cards. So here between the middle. These are black cards, these are the red cards. Hold a couple up. Oh, there's a red card, 7 of diamonds. Up, 3 of clubs, black cards. So that's what I'm talking about. They do have colors. So if we start talking about, well, what's the chance that it's a red card? Just say no. All right, so my first question that I'm going to ask someone, I've got a deck of cards. The cards are random. If you're curious, you need to shuffle cards to make them random. A lot of you know how to shuffle. Don't laugh, I'm terrible at shuffling cards. Stink at this. Look at that. Like, pretend like I yeah, I just shuffled them. But if you're curious, how many times should you shuffle the cards to make them totally random? The answer is 7. They actually did studies just to find out. To make them all truly random, make all these cards truly random, you should shuffle at least 7 times. So if you are a card player, next time you play cards, just know that. You know sometimes people just shuffle once or twice, and they dish them back out. They're not really random. They're not really random. To get them truly random, you got to do it at least 7 times. After 7 times, it's meaningless. You know, it's needless. So just make sure you shuffle at least 7 times. All right, so these have been shuffled. All right, the question is, I'm going to select one card. What's the probability I select a 7 from the deck. Oh, I can make it a fraction, right?
Mm-hmm.
What's the denominator?
52.
52. Very, very good. Everyone 52 for the denominator, right? 52 possible outcomes. Now, watch me screw this up. You gotta fix this. Because I get this on tests. Look. Okay, 7 out of 52.
4.
That's not right, is it?
4.
Let me get that out of the way. How many 7s are there in the
4.
deck? We got a 7 of clubs, 7 of spades, a 7 of diamonds, and a 7 of hearts. There are 4 7s in the deck. Let me fix that. 4 out of 52. That's a nice answer. Although a lot of you probably want to reduce that. So you can reduce 452 to be 1 over
13.
13. So I'm going to take the squiggle. I'll round to 2 decimal places. What do you get on the calculator?
8.0. Also, 0.076.
0.076. So I could write that as 0.08
Yeah.
with the squiggle. My final answer, or
8%.
8%. Cool. And I know we've talked about like approximately exact. These are exact. Like that's exact. But we're getting an estimation. Like, hey, you got roughly an 8% chance.
So we could use any of those answers.
Exactly.
Okay.
You know, if you do like a my stat lab problem, they might go up the 3 decimal places. Okay, we'll write the 0.076. But these are great. So I'm saying, if I really did this, I'm gonna pull the card right now. What's the chances this is a 7? There's an 8% chance. That's not good, is it? It's probably not gonna be a 7, is it? Did I win?
No.
I lost. What did I jack? Oh, jack hearts. I lost. I only had an 8%. Right? If they're truly random. All right. So now, my next one. Let's probably select a 5 or a 9. Now, this is a new word. So let me circle this. Or. The 2 words you hear with probability, or and and. Or and and. Well, here comes this word or. When you hear this word or, basically, everyone, I'm not making a rule up here, but this word or, when you hear it, you're basically adding probabilities. I mean, throughout all probability, when you hear this, what's the chances this or this occurs? What's the probability this or this occurs? I want you to think addition. I want you to think summation. I'll put the rules up eventually. But that's what we're thinking. Like in this case, I'm like, I'm going to have to add these 2 probabilities. All right? And then I'll put the rule up. I'll put the rule up, but I want us to do it without it first. We're thinking addition. So I guess that's the probability I'm getting a 5, plus the probability I'm getting a
9.
9. Well, let's start here. 52 cards in the deck, that's my denominator.
Mm-hmm.
Is that right? Because I get that on test.
No.
Good. What's wrong with the 5?
It should be 4.
There's not 5 5s in the deck. That 5, I'm talking about the actual what? The 5. Can I find one in here? Let's see if we can get a 5 out of this mess. Take me 3 minutes just to find the 5. There's a 5. 5 or hard. I'm talking about that. But there's only 4 of these in the deck, right? There's only 4 5s in the deck. So that's a 4 out of 52. Nope. That's good. Now, how many 9s are in the deck?
Same, 4 out of 5.
The same. And we just add them. So my final answer, I'll just put a wall here so it doesn't interfere with this. I'll just put my final answer,
8 over 52.
8 over 52. I have an 8 in 52 chance. My probability is 8 out of 52. Reduced a fraction, what would that be?
0.213.
2 13ths?
Yeah.
Hey, anybody want to know how to reduce a fraction on a calculator? A lot of you know, but some might not know. If I hit 8 divide 52 on a calculator and I hit enter, right? Don't I get a long decimal? But what if I hit math 1? I hit math 1, which is called the frac button, then I hit enter. What will it do? It will reduce the fraction. Now, you want to try it? If you want to write reduced fractions? You know, you could, I know you all know how to reduce fractions, but if you're like, I'm going to let this tool do it. I get 8 divide 52, this long decimal pops up on my calculator, I hit math 1 frac enter, I frac it. Think of it as a verb, I'll frac it. It's going to reduce the fraction for you. What's that as a decimal?
0.15.
0.15, thanks Gary.
So that should be 0.2. Yes. No, it's 0.16.
Oh, what was after the 5?
538.
Oh, sorry. Yeah, I guess I'll round down to 15%. You could though. If you wanted to round up, you surely could.
Okay.
You really could. You go, hey, 15 or 16%. I'll round up to 16%, like the 538. That number after the 5 was a 5 or higher.
Yeah.
But absolutely, you're like, well, I just wanted to round up. You totally can. So when there'd be a 15% chance of getting a 5 or a 9, can I do it? Come on. Did I win?
No.
I lost. But it had to be a 5 or a 9. Well, it was neither. It was neither. That one, this is the exact answer to this problem. I didn't even write the rule up. But I'm about to introduce the rule, but this is how you do the probability if your two events are, ready? Disjoint events. So here's the first funny word for today. These two events are called disjoint events. What are disjoint events? This event here, selecting a 5 from the deck, and this event here, selecting a 9 from the event, are called disjoint events. Well, what's the textbook definition? Disjoint events have no outcomes in common. Yep. They share no outcomes. They have no outcomes in common.
So is this the same thing as like in discrete math or and you did?
Yeah, exactly.
Okay.
But that's the textbook definition. You go, what are disjoint events? They're two events that have no outcomes in common. Well, everyone, that still sounds confusing, doesn't it? So can we break that down and make it very simple? Ready? I'm just going to pull out one card out of the deck. I'm not going to show it to you. Is it possible for this one card to be a 5 and a 9 at the same time?
No.
Disjoint events. So would you remember that? If you were ever confused about what are disjoint events, I want you to go back to this example and say to yourself, and hold up, and think of me holding up this one card going, this card here cannot be a 5 and a 9 at the same time. That means they're disjoint events. They have no outcomes in common, right? But see, I think you get this. Like, could this be a 9 and like a heart at the same time? Think about that. Is that possible? Oh yeah, so those are not disjoint events. Let me say it again. That's why we like, it's good to learn from cards. You go, can this be a 9 and like a heart at the same time? You're like, oh, that could happen. So those two events would not be disjoint. But these are called disjoint events. And when you have disjoint events, you just add them. All right?
Like mutually exclusive, right?
Yeah, that's another word for this. I'm going to write it up right now. Another word, it means the same thing as disjoint events. Are mutually exclusive events. So both of these mean the same thing. These two events are mutually exclusive. You may have heard that phrase before. So disjoint events are mutually exclusive events, right? The events selecting a 5 and a 9 from the deck are disjoint events. So in terms of probability and the probability rule, if you have disjoint events and you got to find the probability of this occurring or this occurring, we're just going to do what? We're going to add them, right? So now you're like, yeah, can you give us the rule though if they're not disjoint? So here we go. I'm going to write it out as events A and B, and here we go, 5.2, the probability of A or B occurring. This formula will account for everything, so we'll call this the general addition rule. Does that sound good? This will be the general addition rule. This works in all probability for all events. It'll be the probability of A plus the probability of B minus, this is going to be funny, A and B. The probability of A and B occurring. But now if you hear this phrase or in probability, you're thinking addition, right?
Mm-hmm.
But now in this part at the end, we're going to have to subtract that out if the events are not disjoint. Okay? But, hey, we can play this safe. We can do this every time. That way you never miss a probability problem. How about we do this every time? So I'm going to do it right now. In this problem, I had probability 5 plus probability 9. We got the answer right, but I'm going to write this. Minus the probability that it's a 5 and a 9 at the same time, right? I want you to subtract that out. Probably a 5 and a 9 at the same time. Okay. That'd be 4 out of 52 plus 4 out of 52 minus, how many ways can it happen?
0.
0 out of 52. There are 0 ways it could be a 5 and a 9 at the same time. So that's what they mean by here. But we'll include this if the two events are not disjoint, right? This will work every time. So our answer is still 8 out of what? 52. So let me give you another problem. And we'll compare it to this problem. Sound good? So great job with that. You're like, that problem wasn't too bad. All right, now try this one. What's the probability you select a 6 or a diamond from the deck? A 6 or a diamond? Well, I think I'm going to have to race this up here. Can a card have a 6 on it and a diamond at the same time? All right, then we're definitely, everyone, we're doing this on a test. We're going to have to go through all 3 of these. We can't skip over this. We need this, right? Because this will not equal 0. By the way, you want to make up your own theorem? If your two events are disjoint, guess what this has to be every time?
0.
0. If your two events are disjoint. Well, these are not disjoint events. So when I'm erasing this, because these two events are not disjoint. So let me start out. I'm going to have to do probability of the 6 plus the probability of it being a diamond. Here, we can just draw a diamond. Minus the probability it's a 6 and a diamond same time, right? 6 and diamond at the same time when I pull out that one card. All right. How many 6s in the deck? 6 of them?
Yeah.
Good. 4. There's 4 of them. There's 4 6s, there's 4 9s, there's 4 jacks, there's 4 kings, etc. Except for diamonds. Hold up. Diamonds! That's all these, right? That's all these. That's all these. How many diamonds in the deck?
13.
13. And now we subtract some. How many cards in that deck have a 6 on it and a diamond at the same time? There's not many.
Just one.
Just one. Everyone agree? There's just one. Can I find it? Well, I found the 6 of clubs. It's in here somewhere. I'll do a quick search. There's a 6 of hearts. I'm looking for it. Come on. There's a 6 of diamonds. Come on up. 6 of spades. It's probably sitting in my vehicle or something, right? I probably only have like 51 cards here. All right. And there it is. There's that one card, 6 of diamonds. I'm going to subtract it. There's only one more. So the answer to this math problem is not 17 out of 52. It's what?
16 out of
16. 4 plus 13 minus 1, 16 out of 52. Or, want to reduce that? 4 13ths. Or, these are equals. Or
31%.
31%. 31%. So 6 or diamond at the same time. Hey, my chances of doing this are still kind of low. Do you agree? Yeah. It's still like, I don't know. 31% chance is not good. Is this a 6 or a diamond? I lost again. I didn't have a good chance of doing it though, did I? I didn't even shuffle these, but if they're totally random, you only have a 31% chance. Hey, super job with that. Hey, one more of these because I know they're kind of tough. You're like, not tough, we got it. King or a face coat? And see, when you read the question, it sounds actually a little confusing.
Isn't king a face card too?
Yeah, because the king is a face, they're like, what's the probability select a king or a face card? And you're like, sounds like a confusing question, but we're going to go through the probability rule and we're going to get the exact answer. Right? We'll go through this rule. So I'll do, what's the probability of the king? I'll add to the probability that's a face card. But I have to subtract out the probability it's a king and a face at the same time. Okay? Hey, how many kings in the deck?
4.
4? Do you remember how many face cards there were?
12.
Yeah, there's 12 because there you got the jacks and the queens and the kings. There's 4 of each of these, so I'm gonna have to do 12. But okay, this is interesting. How many cards in a deck have a face on it and a king on it at the same time? 4 of them. And we'll get our answer. This question may have sounded a little confusing, but we're gonna get the right answer. 4 plus 12 minus 4 is just, oh, it's the same odds as this. It's the probability of just getting a face card, yeah. Just sounded confusing the way it was worded. 12 out of 52, or if you reduce that, that's 3 out of
13.
13.
I didn't get you the last one. 4 out of 12. How did you get? 12 is like 3, 3, 3, 3, 4. Okay.
Yeah, right?
Okay.
3,
3,
3 of these, 3 of these,
and
and 3 of these.
Gotcha. 4. That's all. Okay.
And we're not including those jokers.
Gotcha.
Has everyone got that? You know the joke, we don't have jokers in this deck. So no jokers, just the 52 cards. Hey, great job with that. Well, that's the general addition rule. I mean, you look it up on a Wikipedia page, you would see that. Cool? All right, hey, so now I'm going to introduce the next rule. But this rule actually comes up in 5.3. Oh, see, I'm about to do this multiplication. I think I should do one rule before that. But I think this next rule is common sense to everyone. I'm going to erase all this. Everyone, if someone said there's a 20% chance it's going to rain today, what's the probability it doesn't rain?
80.
80%? Is that agree? That's called the complement rule. That's called the complement rule. So there's actually a rule for that in probability. Let me just say it again. If there's a 20% chance it's going to rain today, then what's the probability it will not rain? 80%. What did they do? I mean, people just shouted it out. They didn't pull out a calculator. They did this in their head. Everything's got to have to what? 100%, right? Do it again. If the probability it's going to rain today is 40%, there's a 40% chance it's going to rain. What's the chances it will not rain? 60%. And you go, yeah, all right. Everything's got to happen. So we're taking 100%, we're subtracting it. If it was decimals, we'd take 1.0 and subtract it. Okay? So the way that's written in the book, the complement rule, and complement is spelled with an E, not an I. The complement rule, we're saying the probability of not A occurring equals 1 minus the probability of A occurring. That's what we're saying. Right? And there's a little Keno lottery game, and I heard there's a 1% chance. 1% chance I could win that lottery game. Look, there's a 1% chance I win the lottery game. Well, what's the chances I'm going to lose
99.
when I play it? See how fast you are? You're like, oh, you would say the probability I do not win would be 1.0 minus this 0.01 of winning. It would be left with this, oh, really, really strong chance, 99% chance that I'm not going to win. Does that make sense? It's called the complement rule. I noticed while I was watching, and this is fine. A lot of you are like, I don't even have to copy that down. Because you understand that logic, right? You understand that totally, this logic of the complement rule. But you're going to notice how powerful this is in statistics and probability. This idea of the complement rule, it's very helpful. It's very helpful for us. When the probability question gets really, really challenging and difficult, we may have to go to the complement rule. All right, so that'll come up. 5.3, we're going to do the multiplication rule. So, hey, I'll put it in quotations again. Or. I said, if you hear the word or in probability, just think simply you're really doing what? Aren't you adding probabilities? But when you hear this word and, basically, would you think
If multiply.
multiplication? Now, these are not rules. I just want you to think this way. Because you read word and you go, what's the probability that he hits the first basket and the second basket? Right? Melo Trimble's at the foul line. He gets 2 shots, right? What's the probability he hits the first or the second? Because if he does that, he can win the game. And then you go, oh wait, to win this game, he's got to hit the first and the second. So what's the probability he hits the first and the second? Those are different probabilities. Those are different chances, and so we got to make sure. With or we add, with and we multiply. So here comes the multiplication rule. This was called the addition rule. Now we got the probability of A and B occurring. But I want this rule from 5.3 starts out with an if statement. All right, I am just going to multiply the probability of A times the probability of B. Look at this. Probability of A and B occurring. Probability of A times probability of B, but it has an if statement before it. And it's going to be a new word. What was the goofy word before? Disjoint events? All right, here comes the second goofy word for the day. If the events A and B are independent events, I'll put a comma, then this is true. So this only holds true as long as A and B are independent events. So we got to talk about what in the world are independent events. I'll let you copy that. I'll let you copy that. That's an important rule. I mean, yeah, you Google the multiplication rule for probability. You get a Wikipedia page that shows up. You're going to see this. But this will not be written solo. You'll have some information about how those two events have to be what's called independent events. So let me define that. And I know a lot of you like to put this in your notes because you're really good at studying your notes. You take great notes. So let me define this in a few words. What do I mean by two events being independent? Two events, A and B, are independent if the occurrence of A does not alter the probability of B occurring. If you don't like the word alter, I can use the word affect. But let me just say that a few times. I'll just say it over and over and over again so you know what do you mean by independent events? Two events are independent events if the occurrence of event A does not affect the probability of event B. If that holds true, then these two events are actually independent events. If the occurrence of A, the happening, does not alter or affect the probability of B occurring. I'll say it again, because I know why you're copying it. What does it mean for two events to be independent events? A and B are independent events. If the occurrence of A does not alter or affect the probability of B occurring.
So do they have to be mutually exclusive then?
No, and they don't have to be mutually exclusive. And I don't even want to throw that word out now, Art.
Okay.
So anybody gets confused, but I love your question because we can think of some relationship between these two, between mutually exclusive events and independent events. But right now, I just want us to really concentrate on this new word, which is independent events. So, everyone, anybody got a coin on them? Let's say I got a coin right here and I'm flipping it. It's going to land either heads or what?
Tail.
Tails. I keep doing it. Now, do you agree I got a 50% chance it's going to be heads? Right. 50% chance it's going to be tails. I keep flipping this. And I keep flipping this, and let's say I win money every time it lands on heads. Do you think if I played it all day, I'd get really good? I'd get really good at this game, and I would improve my chances of it being heads? No. That's because the events of just flipping that coin are independent events, right? The occurrence of the first 3 times I flipped it did not affect the what? The probability that I would win later. Do you agree? 5 hours later, everyone, I just keep putting, you're still, Professor Messenger, stop. Your chances of it being heads is still going to be what? 50%. They're called independent events. Now listen to this. Let's say I said event A is earning a bachelor's degree. There's a lot of people in this room, you're going to finish your degree here or working on your bachelor's degree, so I'm just going to put earning a bachelor's degree. That's event A, and I'm talking about event B. Just earn more than $100,000 in a year. And these are my 2 events. Well, I hope you agree with me that these 2 events here are not independent. Because earning a bachelor's degree, all right, can actually affect my chances of making more than what? $100,000 a year. We all know what? It's not guaranteed. I mean, do you agree with me? Who knows people who don't have bachelor's degree that make more than $100,000? Me too. And they make millions, don't they? Right. But we're saying it's all about this word chance and likelihood and probability, right? That's the wording. So that's why right here I get this word probability. 2 events are independent events. If the occurrence of A affects the probability of B, then those events are not independent, they're actually dependent, right? The idea, yeah, you're in a brush, actually have a chance of making that $100,000 per year, have better odds of that. We're not saying it's guaranteed though. As you can see, everyone's like, hold up. I know a person, they got their PhD, and they don't make $100,000. But I know my other friend, I know this person, and they make $52 million a year. Yeah, and they didn't even finish high school, right? But it's all about probability and chance. Cool. All right, so, hey, have you ever seen, I'll step away from the cards now. Have you ever seen a roulette wheel? Mm-hmm. So I need to show you an image of this. I was going to pull it up there, but this would be quicker because there's a picture of this in a textbook, and a lot of you have your textbook. And when on page 266 at the top, there's a picture of a roulette wheel. So at the top left of page 266, I figure that'll be faster. You can see this actual roulette wheel. And I'm going to put down what's on this roulette wheel. There are numbers, but there's colors, reds and blacks, and there's a green. There are 18 reds. There's 18 black slots, and there's 2 green slots. You go, do I have to memorize that? No. I know. Understand the cards, but you wouldn't have to memorize this. But there are 18 red slots. There are 18 black slots. There are 2 green slots. And do we have casinos in Maryland? Mm-hmm. Yeah. Do they have roulette wheels? Yeah. And a lot of people go over and play it. And it's like, all right, I'm going to bet $5 on black. And he drops the wheel spins, right? Drops the little ball in there, and it circles around. The wheel starts slowing down, and that little ball falls finally in a slot, right? And if it's a red slot, okay, black slot, whatever, and you're saying if I win or lose. So here's my question. Are these events of me just playing this game over and over and over again, are those independent events? Mm-hmm. Do you agree? I mean, it's the idea, like, if I keep playing it, I'll get better at that game. No. Yeah, you're all like, no, they're independent events. It's like flipping the coin. Right? The occurrence of the first 5 times I played it does not affect the what? The next one. Although, everyone, if you're curious, in this world, has that ever happened where they weren't really independent? Yeah, actually, I mean, this is a true story. True story. When some of the roulette wheels, especially in Europe, over time, made out of wood, over time can what? Warp a little bit? Mm-hmm. Might not be totally level. And so this family, started with the father, he would go in and they would just sit there near the roulette wheel and write down on a piece of paper all the numbers that came up for like an hour straight. Right? They go back to the hotel room, tally up all the numbers to see which numbers are coming up more often than the others. Now, why was this happening? Because what happened to that level roulette wheel? It was made up, it kind of warped a little bit. And when they made thousands and thousands and thousands of dollars doing this, because they knew which numbers would come up what more often. So true story. I mean, you can probably find this on YouTube. Eventually, he wanted to do this in Las Vegas. So and then when he took his family out of college to work with them, he took them out of college. They would do this. They'd go to casino, working like Paris. And they would just write all the numbers, go back. What have we got? All right, let's bet money on either red or bet blood on sevens. Made a ton of money. But when he went to Las Vegas, okay, don't they have cameras everywhere and stuff like this? Oh, they spotted him like within an hour. We got people counting the stuff. They're watching over here and all that. Even though I'm sure they study that roulette wheel every day, make sure it's totally level. But they caught him, and because they might have been doing something else. They might have been counting stuff like even the blackjack cards. So when they put him up, and when he almost had he didn't have a heart attack, but he really did have a serious episode and stuff. So he basically retired after that. But so can I just throw you out of a casino? Yeah, he wasn't doing anything illegal. That's what I like about this. He's just thinking of. I like that he's using probability. But they have the authority to just throw you out of the, and say, hey, now we get your face. We don't want you to come back.
Didn't a bunch of kids from MIT did that?
Oh, that's a great story. Let me see the movie 21. Let me see the movie 20. Yeah. So he's talking about the kids from MIT doing stuff like this.
Yeah.
But this, I want we're going to consider, you got a level board, it's basically independent. So here's my question. What's the probability? It falls on red 3 consecutive times. So that means that when I'm going to play this game 3 times in a row, I'm betting on red each time. I'm betting on red, I'm betting on red, I'm betting on red. I want to know the chances that I can win this 3 times in a row. That it's going to land on red, then land on red, and land on red. By the way, you read this. 3 consecutive times means 3 times in a row. In a row. That's what it means. So when you read this, you might be thinking, do I have or do I have and? And you may want to put this in your own wording. So when you and I read this, what's the probability it falls on red 3 consecutive times? That doesn't mean it lands on red, or then it lands on red, or then it lands. This means it lands on red, and
red.
Lands on red, and lands on red. Do you follow me? So that's why we're going to multiply these. And we said we're allowed to because they're independent events. So I'm going to get my parentheses right. Okay. I'm getting it all ready. Now what's the chances it lands on red? Remember, we got to make this a fraction.
So
What's the total number of events here?
18 over 38.
So we're looking at the total number of slots, right? What's 18 plus 2?
38.
So hey, if I did present this on a test, because I said you don't have to memorize that, but you would have to add these up to get this what? 38, right? All right, now, how many red slots were there?
18.
Okay. So isn't that the chances it lands on red the first time? But then I just do what? Now when I'm writing this out the long way, I know there's people in the class right now, they go, I've got a faster way to type this on a calculator. But I'm not going to, I'm okay, I could type it out like this on my test, I'm going to get full credit. I'll just take it slowly, just make sure I put these parentheses, right? Don't round early though, right on? Like we're going to write off, I'll do it like that. Now, who in this class has just a slightly quicker way to type that in on a calculator?
Cube.
I heard it. And can I write this as 18 over 38, close the parentheses, raised to the third power, right? So I'm going to write it that way in case someone in here prefers that. I just ask you to be careful because, watch this. I would hate for a student to go, oh, I know how to do this. It's 18 over 38 cubed, and they accidentally do that. No, that's not right. That is not right. Does anyone see that? Do not do that. You're going, oh, I'm not doing that. That's not what it means. It means, ready, raise to the third. So how do you get this raise to the third on your calculator? There's a caret button. There's a caret button. It means it'll raise it to the third power. 18 over 3. So I'm curious, what comes up?
11%.
So I'm going to squiggle. Because I don't think, Autumn, in this case, the numerator and denominator get so daggone big, let's just go ahead and approximate what this comes out to be. 0.11, what was after the 1-1?
It's like 0.106, so 11%.
Oh, so we came out to 0.106. So we're saying there's roughly an 11% chance, right?
Mhm.
That this happens. Cool? I love it. Now, if you want to do it this way on your, that's fine. Just be careful, true? But there's nothing wrong with doing it the wrong way. Now, something else. When you do this, make sure you put what around the 18/38. Because you know order of operations? Boy, is that order of operations so important in statistics class. Because we're always using these calculators. And if I didn't put the parentheses, the calculator, if I wrote 18 divide 38, raise the calculator's only going to put the 38 to the third. Does that make sense? Cool. All right, I got another one. What's the probability it falls on red 6 consecutive times?
That's even less.
What's the probability it falls on red 6 consecutive times?
18/38 to the power 6.
Well, what would be the long way? 18/38. 18/38. You're like, man, you're doing it the long way. Well, I'm playing it safe. 18/38, and finally, do you all agree? Every time I keep multiplying these, 1, 2, 3, 4, 5, 6, the odds keep getting smaller and smaller and smaller. I love it.
So
But what's the fast way?
1%. To the power
Ta-da. 6 power. Point 0
6. 0.
0
No, 0.011.
0.011, so roughly a
1%.
1% chance. So everyone, can I ask you a question? Would this be unusual? How about for our class, we're going to consider anything under 5% chance unusual. Does that sound good for our class? So that'll be our standard. We'll say anything under 5% chance we'll consider as unusual. So would it be unusual for this to happen?
Yes.
It would, but could it happen? Yeah, you go, it could happen, but it'd be very unusual. You only have a 1% chance of that happening. Cool. Hey, we barely got into 5-3. So I didn't want you to think like, oh, I can do all the 5-3 sections. I mean, we just barely got into it. So next class, we really did 5-1, 5-2. We're going to start with 5-3 on Monday. And have a great weekend.